Hello, welcome to this video. I'm Zhenyi. I'm a PhD student at Vienna University of Economics and Business. Today in this video, I'll start by introducing the Solow model with technological progress and population growth. After that, we'll bring theory to practice by simulating the model in Matlab through two axes. Now let's get started. We'll focus on the Solow model with technological progress and population growth. The aggregate output of a country follows a Cope-Douglas form, utilizing two inputs, capital and labor, raised to the power of alpha and 1 minus alpha respectively. The labor equals to the population size and growing. The labor productivity A is labor augmenting and growing, and capital K is accumulated. We assume technological progress at rate JA and the population grows at rate N. The capital accumulation equation is this one. And finally, we define variables in efficiency unit as the variable divided by AL. All of these settings are standard. For more details, you could check the YouTube channel of Professor Cross-Prisoner. With all of the above defined variables at hand, we can derive the dynamics, that is, the derivative with respect to time, of the 6 variables. Please note that variables with tilde are in efficiency units, variables in lowercase letters are per labor unit, and variables in capital letters represent aggregate values. Here I write down the dynamic equation for output and capital per efficient unit of labor, output and capital per worker, and aggregate output and capital. The differential equations of these 6 variables with respect to time tell us how these variables change over time, and we will use these dynamic equations to solve the Solow model. Then in the steady state, the change of k tilde should be 0, so we can solve for q tilde at steady state from the dynamic equation. Then if we have already have the value of k tilde star, which is the value of k tilde at the steady state, based on these dynamic equations, we can solve for all relevant variables value and growth rate at steady state. Here I list all of these values and growth rate in this table. We could state that at the steady state, the capital and output per efficiency unit of labor should be constant. The growth rate should be 0, and the capital and output per worker will grow at a rate of JA, and aggregate capital and output value will grow at a rate of J plus N. Okay, now based on the Solow model we have learned, let's work through two axes to deepen our understanding of the model. The first axis, in the first axis, we should choose realistic parameter values and determine the initial conditions of capital, output, and population and technology. Then we can implement the model numerically and solve for the trajectories of these 6 variables from time t0 until the economy approaches to the steady state. Then in the second axis, we assume that the economy is initially at the steady state. So we will use the steady state values from the first axis as initial conditions, and then we assume that at time t equals to 20, the economy experiences a natural disaster that destroys 20% of the total capital stock. And I will show you the transitional dynamics until the economy is back at the steady state. Okay, now let's shift to the Matlab and see how to simulate the model. Okay, now let's have a look at the first axis. To implement Solow model numerically and solve for the trajectories, in general, we should first set the parameters for the model and initialize the rates of time, capital output, population, and technology. Then in the simulation loop, we define changes of variables using differential equation, what we have seen in the slides, and we update variables accordingly over time. Then finally we plot the results. Let's have a detailed look. For parameters, alpha is the output elasticity of capital. The value of alpha is usually between zero point 0.3 to zero point 0.4, here at 0.35. As its saving rate, it varies a lot across countries. Countries such as United States has a relatively low saving rate, it's usually below 20%. Countries such as China usually has a high saving rate, it's usually over 40%. On average, I choose 25% as saving rate, as world saving rate, and I think it's a reasonable value. The delta is depreciation rate is usually between 5 to 10%. I choose 7% here. And I set the population growth and technology growth rate as 1 and 2% respectively. I set the time period as 100 to say whether in the 100 time period the economy can approach to the steady state or not. For the initial condition of output, capital, population, and technology, I searched for the real data in 2023. The world output in 2023 is more than 86 trillion US dollars, and the new capital formation in 2023 is more than 1 trillion US dollars, and there are more than 8 billion people in the world in 2023. So based on the real data, I set the capital greater than the labor force. I set the initial capital stock as 400 and the labor as 100, and use the aggregate output function. Given the value of alpha, I calculate the aggregate output level is around 250. So I use these numbers as the initial value of output, capital, and labor. And I set the technology level equals to 1 at the beginning. So we need to initialize variables. The time vector t is starting from 0 to capital T is 100 in our case. And I allocate an area of zeros to capital and output. And all of these zeros will be replaced by a real number that calculated in the simulation rule. And I set the value for the first element of these vectors as the initial value of output and capitals. For here, for y tilde, k tilde, and output and capital per worker, I use the definition of these variables to calculate the value of their first elements in this array. And we should know that the population is growing at a rate of n, and the technology is growing at a rate of g. Okay, then in the simulation loop, we should set the time period from 1 to t, and here in the differential equations are just what we have seen in the slides. Using all of these differential equations, these equations will tell us how these variables change over time. We are interested in the y tilde, k tilde, their output and capital per efficiency unit, and k and y are output and capital per worker. The capital K and Y is the aggregate capital and output. Then we need to update these 6 variables accordingly. So for example, the y tilde in the next time period equals to the value of the y tilde in this time period plus the change of the y tilde in one time period multiplied by the length of the time period. And don't forget to let labor and technology grow over a rate of n and j respectively. Okay, so after this simulation loop, all of these arrays we initialized at the beginning will be replaced by the value calculated in the simulation loop. So we will get 6 arrays of the output and capitals, and then finally we can plot all of these 6 variables with respect to time period respectively, and say the trajectory of different variables in one graph. Here I calculate the steady state for k theta and y theta just for drawing the steady state line in the plot. Okay, so let's have a look at the plot. Here we could say that the output per efficient unit of labor and the capital per efficient unit of labor gradually approach to the steady state after like a 70 time period. While the output per worker and capital per worker will keep growing at a rate of GA. If you remember, we have seen it in the slides. And the aggregate output and aggregate capital will keep growing at a rate of GA plus N. Okay, then let's have a look at the second exercise. When there is a natural disaster happened at t equals to 20. So the first step is that we should set the parameters. We let them are the same as they are in the first exercise. For the initial condition, because we assume that in this exercise, the economy is starting from the steady state, and we will use the steady state value from the first exercise. We set the initial output, capital, population, and technology as the value of as the steady value in the first axis. Then similarly, I initialize some variables, the time, output, and capital, and I allocate a value for the first element of this arrays, just the same as what we have done in the first axis. Then in the simulation loop, firstly, we need to determine whether the time period now is equal to 20 or not. Here you could say that I check whether I equals to 21 is not 20. That's because we could say here the time period starting from 0, not 1. So it means that you could imagine you pull the x-axis one step to the right hand side. So we need to check whether I equals to 21, and when I equals to 21, actually t equals to 20. If it's at the time period 20, then the total capital stock should be destroyed by 20%. So the capital stock at t equals to 20 should be equal to the 80% of the total capital of the original capital stock. And the capital accumulated in this way, what we have seen also in the slides. And then I update variables accordingly, mainly according to the capital accumulation. Then finally, we use the definition of the output and capital per worker and the output and capital per efficient unit to calculate the value of these 4 variables. So we will get the value of capital K and capital Y directly from the simulation rule, and then we use the definition of the other 4 variables to calculate the value of the 4 remaining variables. Then finally, we will plot the result. Okay, now let's have a look at the result. Okay, here we could say, let's start from this graph, the capital per efficient unit of labor. We could say in the first 19 time period, the capital per efficient unit is close to the steady state. At the time 20, it's sharply dropped. It's because of the destroy of total capital stock. And we could say that for all capital-related variables, the value of capital per worker and aggregate capital also dropped at time 20. However, we could say that for the output per efficiency unit of labor, actually the value of the waiting time dropped at time 21, not 20. That's because in the code, you could say that the destroy of total capital stock in the time 20 at the time 20 will affect the output level only in the next time period, not in this time period. Okay, so now we finished the two exercises, and in this video we briefly introduced the Solow model with technological progress and population growth, and we took two exercises to better understand the model, and we could say how to simulate the model in Matlab and how to find the trajectories, and how will the economy react after a disaster, after an external shock. Thank you for watching.